Myself, Saravanan, Assistant Professor, Department of Electronics and Communication Systems, AJK College of Arts and Science. Today I am going to discuss about the 8085 microprocessor instruction set. So the microprocessor having the various kinds of languages we are using here. So mainly we are using the assembly language program. By using the assembly language program only we are going to write the program for this 8085 microprocessor. So basically we are having the three different types of languages. Assembly language program, then machine language program, and then the high-level language programs we are using. So high-level language programs we are using for the computers for writing the program. If it is a low-level language program means the binary numbers will be used for writing the codings. Assembly language program means we are using the hexadecimal code values. Here in this 8085 microprocessor we are going to use the assembly language programming codes, that is the hexadecimal numbers. So hexadecimal numbers are from 0 to 9 and then from A, B, C, D, E, F. So these are all the 16 values are available for this assembly language program. So otherwise we can say it is said to be hexadecimal number systems we are using here. So by using these hexadecimal number systems we are going to write the program. Before writing the program, the various kinds of instructions are available for this 8085 microprocessor. So first we are going to discuss about the instruction set of this 8085. So what is an instruction? An instruction is a binary pattern designed inside a microprocessor to perform a function. What kind of function? It will be represented by the user. So based upon our input, the microprocessor will perform the operation. That is the function of this 8085 microprocessor instruction. There will be various kinds of group of instructions will be available for this 8085 microprocessor. That is said to be an instruction set. By using this instruction set, we have to read totally 246 instructions are available in this 8085 microprocessor. So each and every instruction will be represented by various kinds of binary values. Either it may be the 8-bit binary number system, otherwise the 16-bit binary values, otherwise the 24-bit binary values are there. So based upon the size of the binary values, it will be classified into 3 bytes. 1-byte instruction, 2-byte instruction, and then the 3-byte instruction. So each and every instruction will have two parts. One is the opcode part, another one is the operand part. So what is an opcode? Opcode represents what type of operation we are going to perform with the microprocessor. That is said to be the opcode. So next one will be the operand part. What is an operand means? The operand always represents where we are going to perform the operations inside the microprocessor. It will be represented in the operand part. So by combining this opcode and the operand part, we can able to do the operations here. So the various kinds of classifications of instruction set is available in the 8085 microprocessor. The first one is the data transfer instruction. So data transfer instruction is always used to transfer the data from one location to another location. That is said to be a data transfer instruction. The second one is the arithmetic instructions. If you want to do any kind of arithmetic operations, then we have to go for this arithmetic instructions. Next is the logical instructions. The all kind of logical operations will be performed inside this processor will be used by using the logical instructions. Next one is the branching instruction. If you want to transfer the program control from one location to another location, then we have to prefer with this branching instructions. The next one is the machine control instruction. If you want to control the microprocessor, then we have to prefer this machine control instructions. So these are the various kinds of instruction sets are available in the 8085 microprocessor. So this 8085 microprocessor is a 8-bit processor. The input and the output will be always in the form of the 8-bit binary data we have to give. So you can able to process the 8-bit binary operations. First is the data transfer instructions. So these instructions are always used to move the data between the registers, otherwise between the memory and registers. By using these instructions, we are going to transfer the data from one location to another location. So maybe these instructions will copy data from source register, otherwise the source to the destination location. So source location to destination location, we are going to transfer the data, otherwise we are going to copy the data. While copying, the content of the source cannot be modified here. That is the important thing in this 8085 microprocessor. Just copying the data from the source to the destination area. Next is the data transfer instructions example. For example, we are using the opcode and operand parts are there. So move will be the instruction for used to transfer the data from one location to another location. The operand part will be varied. So either we can able to transfer the data from source register to the destination register, otherwise the source register to the memory content, otherwise the memory content value will be transferred to the destination register. So these are the three different types of methods are available for transferring the data by using the instruction called MOV instruction. So this is always a 1-byte instruction. By using this 1-byte instruction, easily we can able to transfer the data very fastly. The operation will be taken place. What is the function of these instruction means? It always copy the data from source to the destination area. So each and every instruction copies the content of the source register into the destination register. Mainly the contents of the source register are not altered here. If any one of the operand is in the memory location, then its location is specified by the contents of the HL registers. Because here we are using the various kinds of registers are there. A register, B, C, D, E, H, L. So these are all the 8-bit registers here. If you want to use a 16-bit data means, then we have to use the register pairs. What are the register pairs available here means? BC, DE and then HL. So these are all the various kinds of register pairs are available in the 8085 microprocessor for doing the 16-bit operation. If it is an 8-bit operation means we go only with the 8-bit registers, otherwise we prefer with the 16-bit registers. Example for the data transfer instruction will be the move B, C. The move B, C represents the C register content copied to the B register. A C register is the source register and B register is the destination register. So another example is move B, M. Here M represents the memory and B represents the register. If I execute this instruction, what will happen means the memory content value will be copied to the B register. So that is the function of these instructions in the data transfer operations. If you want to transfer the data directly to the register, otherwise directly to the memory means, then the instruction is MVI. MVI represents move immediately. The 8-bit data value will be directly transferred to the destination area. So the operand part will be RD, 8-bit data. Another one is M, 8-bit data. RD represents the destination register, the M represents the memory. So each and every time directly the data value will be transferred to the, otherwise it will be copied to the destination location. This 8-bit data is stored in the destination register, otherwise it will be stored inside the memory content area. If the operand is a memory location, its location is specified by the HL register pair only. For example, if we are using a MVI M, data means the particular data value will be stored to the HL register pair memory location address. So first the cursor will directly goes to the HL register pair, it will find out what is the memory address is available. In that memory address only the 8-bit data value will be stored. That is the function of this instructions we are using. So example MVA B, 57H. That H represents it is an hexadecimal value and 57 is the hexadecimal value. When I execute this instruction, what will happen means the data 57 hexadecimal value will be copied to the B register. So that because here the B register is the destination register, the source will be the data. The next instruction is MVA M, 57H. The 57 is the hexadecimal value, it will be copied to the memory location. So memory location means the program control directly goes to the HL register pair. There will be a 16-bit memory address is available. In that memory address, the 57 hexadecimal value will be copied. That is the function of this data transfer instructions. Next is the 16-bit address. We are using the operand part. Previously, we are discussing about the 8-bit operand part. Now we are going to discuss about the 16-bit operand part. So the opcode is LDA and the operand part will be the 16-bit memory address we have to use here. This instruction is always used to load the accumulator content directly to the specified value. So example LDA, then we have to write the 16-bit memory address value. When I execute this instruction, what will happen means the data value will be stored inside the 2034 memory location copied to the accumulator. Another name for the accumulator is A register. So inside the A register, the data value will be copied. The data is always an 8-bit data, but the memory address is a 16-bit memory address. The content of a memory location, the specified by a 16-bit address and the operand part are always copied to the accumulator. That is the function of this data transfer instruction. While executing this instruction, the content of the source cannot be destructed. The next one will be the LDAX instruction. So this data transfer instruction is indirectly going to transfer the data. That is the function of this LDAX instruction. It always loads the accumulator indirectly. The operand part will be any kind of register pairs we have to use. Either it may be the BC register pair, otherwise the DE register pair we can able to use here. So the content of the designated register pair point to a memory location. The instruction copies the content of that memory location into the accumulator. The content, either the register pair or the memory location, cannot be altered here. So example for this instruction is LDXB. So here B represents the BC register pair. Instead of B, if I use LDXD means it represents the D register pair. So that is the data transfer instruction for this LDX instruction. Next is LXI instruction. So this is also used for transferring the 16-bit data here. So this instruction is used to load the register pair immediately. This instruction always loads a 16-bit data into the register pair. That is the function of this LXI instruction. The output is LXI and the operand part is the register pair, otherwise the 16-bit data directly we can use here. So example, LXI H, 2034H. The LXI H represents an HL register pair. The 2304 will be the memory address. This memory address content value will be copied to the child memory location. The next data transfer instruction is LHLD. The LD will be the load HL register pair directly. The operand part is the 16-bit address value. When execute this instruction, what will happen means the particular instruction will copy the content of the memory location pointed by the 16-bit address into the register L. The two registers we are using here, one is the L register, another one is the H register. The 16-bit value, lower order value will be copied to the L register and the higher order value copied to the H register. That is the function of this LHLD instruction. So this is also a 3-byte instruction. Then LXH also has a 3-byte instruction. So depending upon this, the number of byte instruction will be varied here. For example, if you use an LDAX instruction, it will be always a 1-byte instruction. So number of bytes will be increased means the execution time period will be increased. The next data transfer instruction is STA. By using this STA instruction, easily we can able to store the accumulator content directly. That is the function of the STA instruction. The content of the accumulator always copied into the specified memory location. It will be exist in the operand part. Example, STA2500. When I execute this instruction, what will happen means the accumulator content value will be copied to the 2500 memory location. So this is the process of this data transfer instruction. So these are all the various kinds of data transfer instructions we are using in the 8085 microprocessor. The next one is the stacks. The STX represents we are going to store the accumulator content indirectly. STA means directly we are going to store the accumulator content. Stacks represents indirectly we are going to store the accumulator content here. The output is STX and the operand part is register pair we have to represent. Any kind of register pairs we can use, either maybe the BZ, DE, otherwise the HL register pair we are using. By executing this instruction, what will happen means the content of accumulator are always copied into the memory location specified by the content of the register pair. So this is a 1-byte instruction. The next data transfer instruction will be the SHLD. So SHLD, we are going to store the HL register pair directly. So previously we are loading the HL register pair, now we are going to store the HL register pair directly here. When execute this instruction, what will happen means the content of the register, the lower order register, the L are stored into the memory location specified by the 16-bit address. The next, the higher order address memory content value will be stored inside the H register pair. So that is the function of this SHLD instruction. The example for this SHLD instruction will be SHLD will be the output part and the operand part will be the 16-bit memory address. Example, consider 4500. So this is also a 3-byte instruction. Next one is the exchange instruction. So this instruction is always used to transfer the data from HL register to DE register pair. That is the function of this exchange instruction. For example, it consists only a output part only. So it will be only a 1-byte instruction. So when I execute this instruction, the content of H register will be exchanged with the content of the D register. Like that, the lower order register L value will be copied to the E register. That is the function of the data transfer instructions. Next one is the SPHL. SPHL represents we are going to use the stack pointer for loading the data here. So it must be copy the HL register pair to the stack pointer. Particularly, the instruction loads the content of HL pair into the stack pointer. That is the function of this data transfer instruction. It is also a 1-byte instruction. Otherwise, we can say it is an implicit mode of addressing mode. Next is the data transfer. In the data transfer instructions, the XTHL instructions. The XTHL represents we are going to exchange the HL register with the top of the stack pointer. The stack pointer is available. It will be represented as SP. When I execute this instruction, what will happen means the stack point value will be incremented by 1. For example, in the HL register pair, if any content is available, that content value will be incremented. The memory address location value will be incremented by 1. That is the function of the exchange instruction here. Next one is the PCHL. PCHL is always used to load the program counter with the HL register content. The content of the register H and L are always copied into the program counter. The content of H are placed as the higher order byte and the content of L will be placed as the lower order value. So by combining this lower order and higher order address values only, we can able to transfer the data for any kind of 16-bit transfer operations. The next one is the push operation. This push operation is always used to push register pair onto the stack here. When you execute this instruction, what are the changes will be taking place means the content of register pair are always copied onto the stack here. The stack pointer is decremented and the content of the higher order register values will be copied into the stack. What are the higher order here means the B, D and then H. So these are all the higher order registers we are using. Once again, the stack pointer is again decremented and the content of lower order registers are copied into stack. The lower order register, C register, E register and then the L register. So example for this instruction is push operation is push will be the output part and the operand part is any one of the register pair we have to represent. Example B. So push B represents we are going to push the content for the BC register pair here. Next one is the pop operation. By using this pop instruction, what will happen means the pop will always use for stack to register pair here. When I execute this instruction, what will happen? The content of location pointed out by the stack pointer always copied into the lower order register here. The lower order register, any one of the register pairs C, otherwise Z or L register will be used here. Next, the stack pointer is always incremented here and the content of location are always copied to the higher order register. Either it may be the P register, otherwise the D register or H register. Example for this instruction is pop is the opcode part and the operand part is H. So this is also a 1-byte instruction. The next one is the out instruction. So out instruction is always used to copy the data from the accumulator to a port with 8-bit address value. If you want to transfer a data to the output port means then we have to use the instruction called out instruction. This is a 2-byte instruction. The out is the first byte and second byte will be the 8-bit memory address value. The minimum memory address value will be 00H and the maximum address value will be F of H. In between the 00 to F of, we have to select any one of the memory address location for transferring the data to the particular port. When I execute this instruction, what happens means the content of accumulator always copied into the IO port here. So this is a 2-byte instruction. Next is the in operation. The in operation is used to transfer the data here. Where it will be transferred? It copies the data to the accumulator from a port with 8-bit address value. In the operand part, we have to specify the 8-bit port address. Through the port address, the data value will be copied to the A register. The content of IO port are always copied into the accumulator. So this is also a 2-byte instruction. So example for this instruction is opcode is IN and the operand part is we can use any one of the memory address from 00 to FF. Next is the arithmetic instructions. Previously we are transferring the data. The next step is we have to do the arithmetic operations here. The various kind of arithmetic operations we can perform here. The first one is the addition operation we can perform, then the subtraction, the increment operation and then the decrement operation. So here directly we cannot be able to do the multiplication operation, otherwise the subtraction operation. Multiplication operation and also we cannot be able to do the division operation here. So addition operation means we can able to add the data here. Subtraction we can able to do the subtraction. Instead of multiplication, how can we do the multiplication here means by doing the repeated addition process. Then only we can able to do the addition process here. If you want to do a division process, then we have to repeatedly subtract the data. Then we can able to perform the division operation. So increment operation is always used to increment the values either by 1 or some other values. Like that for the decrement operation, we can able to decrement the values by 1. So these are the functions of the arithmetic instructions. First is the addition operation. So here by using the addition operation, we are going to add the data. Any one of the register content will be directly added with the accumulator. So any kind of addition, otherwise the subtraction operation, one of the register content, otherwise the directly data will be added only with the accumulator. Otherwise we cannot be able to do the addition operation or subtraction operation here. So any 8-bit number, otherwise the content of the register, otherwise the content of memory location can be added to the content of only with the accumulator. During this addition process, where the output values are stored, the output values, otherwise the result or otherwise the sum is always stored inside the accumulator only. Another name for the accumulator is A register. Directly we cannot be able to add 2 register contents. So subtraction, the same process will be used for the subtraction process also. So directly we cannot be able to do the subtraction process by using directly the registers. Instead of that, one of the data will be available in the A register, the another data is available in the maybe register, otherwise the memory location, otherwise it will be stored in the accumulator. So based upon this only we can able to subtract the data here. During the subtraction process, the output value is always stored inside the accumulator only. If you are doing the addition process, the sum will be generated. If you are doing the subtraction process, the output value will be generated as a difference value. That difference value will be stored inside the accumulator. So here the subtraction will be performed in the form of the 2's complement method. Instead of using the 1's complement method, the subtraction process in the 8085 microprocessor will be done by using only with the 2's complement subtraction method. If the result is negative, it will be stored in the 2's complement method. So directly we cannot be able to subtract the two registers here. Next is the increment and decrement operations. The 8-bit content of a register, otherwise the memory location, can be incremented or decremented by 1. That is a function of the increment operation, otherwise the decrement operation. The 16-bit content of a register pair can able to increment, otherwise it will be decremented by 1. Either we can do the 8-bit operation, or otherwise we can do the 16-bit operation for the increment operation and also the decrement operation. Increment or decrement can be performed on any register or a memory location we can perform here. So arithmetic operations, or otherwise arithmetic instructions. So ADD is the arithmetic instruction. It is an opcode part, and the operand part is we can use the register, otherwise the memory. R represents the register and M represents the memory. When execute these kind of instructions, what will happen means these instructions add the register, otherwise the memory content to the accumulator. That is the function of this arithmetic instruction ADD. When you execute this instruction, what happens means the content of register or memory are added to the contents of accumulator. The result will be always stored inside the accumulator. Another name for the accumulator is A register. If the operand is memory location, its address is specified by the HL pair. Based upon this output value of this arithmetic instructions, what will happen means the flag values will be changed here. So each and every flag status value will be changed depending upon the output of this addition instruction. Example for this addition operations are ADDB. ADDB represents A implies A plus B. The A register content value will be added with B register and the output value stored inside the A register. That is the function of this ADDB instruction. Next is ADDM. ADDM represents we are going to add the accumulator content with the memory content and the output value stored inside the A register. These two are the 1-byte instruction. Add B is a 1-byte instruction and add M is also a 1-byte instruction. Next arithmetic instruction is ADC. So previously ADD instructions will be used to add only the two datas only. If you want to add the datas with carry means, then we have to use the instruction called ADC instruction. This ADC will be the opcode part and the operand part is either we have to use a register or memory. The register will be any one of the 8-bit registers we can use. Either it may be A, B, C, D, H, E, otherwise the L we can use. Otherwise the memory directly we can use. When you execute this instruction, what will happen means these instructions used to add register, otherwise the memory to the accumulator with carry value. Where the carries exist, previously the carries exist inside the carry flag. So depending upon the carry flag status value, the output content value will be changed in this ADC instruction. The content of register or memory and carry flag value will be added to the content of the accumulator here. The sum value will be stored inside the accumulator. If the operand is in memory location, then its address is specified by the HL register pair. All flags are modified to reflect the result of the addition here. All flag values will be changed here based upon the output of this addition with carry instruction. Example for this instruction is ADC is the opcode part and the operand part is any one of the registers we can specify. ADCP, ADCM, ADCD, ADCE or any kind of instructions we can able to use here. The next arithmetic instruction is ADA instruction. So add immediately. Immediately represents we are going to add the data directly with the A register means then directly we prefer with the ADA instruction. So this is a 2-byte instruction. The ADA is the first byte and second byte is the 8-bit data which will be added with the A register. So this instruction is add immediately to the accumulator. That is the function of this arithmetic instruction ADI. The 8-bit data is added to the content of accumulator. The result is stored in accumulator here. All the flags are modified to reflect the result of the addition process. Example for this instruction is ADI FFH. FF is an hexadecimal value to be added with the A register. So previously we are adding the two register contents. One of the register content value will be added with the A register. But now directly the data value will be added with the A register. That is the function of this instructions we are using. The next arithmetic instruction is with carry. So immediate operation will be taking place. At the same time, we are going to add the carry value here. That is represented as ACA. Add immediately to accumulator with the carry here. The operand part consists of the 8-bit data. The 8-bit data directly added with the A register and also it will be added with the carry flag value. The 8-bit data and the carry flag are always added to the content of accumulator here. The result is stored inside the accumulator. What about the flag status means? Depending upon the output of the accumulator, the flag status values will be changed to set condition, otherwise the reset condition. That is a function of this instruction. This ACA instruction is also a 2-byte instruction. Next one is the DAD instruction. So DAD represents it is a double addition. What we are going to perform by using this instruction means, if you want to do any kind of 16-bit addition operation, then we prefer with this DAD instruction. The opcode is DAD and the operand part is register pair. By using this instruction, we are going to add the 2 register pair content values. The HL register pair will act as an accumulator here. So any one of the register pair content value will be added with this HL register pair and the sum value will be stored inside the HL register pair. That is a function of this instruction. If the result is more than 16-bit value means, then automatically the carry flag will become set condition. The other flags cannot be changed here. So example for this instruction is we can use DAD as the opcode part and the operand part will be the any register pair, either it may be the BC or DE, otherwise the HL. The next arithmetic instruction will be the subtraction. So subtraction instruction is SUB. SUB represents, it is used to subtract the values. Any one of the register content, otherwise the memory content value will be subtracted from the A register. That is the function of this subtraction instruction. So this is a 1-byte instruction. Example for this instruction is SUBB or SUBM. M represents the memory, the B represents the register content. Based upon the output of this subtraction process, all the flag values status will be changed. Either it may be a set condition, otherwise it may be the reset condition. That is the function of these instructions we are using. The next is SBB. SBB represents subtraction with borrow. So SBB is the opcode part and the operand part will be either it may be the register, otherwise the memory. If you want to subtract with the previous borrow value means, then we prefer with the SBB instruction. By using this instruction, the content of the register, memory location and borrow flag will be subtracted from the content of the accumulator. Based upon this operation, the output value always stored only inside the accumulator. That is, the difference value will be stored inside the accumulator. If the operand is memory location, its address will be specified in the HL pair. All flags will be changed here based upon the output of the subtraction operation. So example for this instruction is SBB or SBB. This is also a 1-byte instruction. Next is SUI. SUI represents subtract immediately. Previously we are subtracting the data from the register. Now directly we want to subtract the data from the accumulator means, then we have to use the instruction called SUI instruction. Subtract immediately from the accumulator. The particular 8-bit data specified in the operand part value will be subtracted from the A register. That is the process of this arithmetic subtraction instruction. The output value will be stored inside the accumulator. At the same time, all the flag status values will be changed here. So example is SUA 45H. The 45H is a hexadecimal value. It will be subtracted from the accumulator and the output value also stored inside the accumulator. The next arithmetic instruction is SBI. SBI represents subtract immediately from the accumulator with borrow value. Previously without borrow we are discussing. Now we are discussing about the subtraction with borrow immediately. The specific 8-bit operand value will be subtracted from the A register and also will be subtracted from the carry value. Then the output value will be stored inside the accumulator. So based upon the accumulator content, all the flag status values will be changed here. So this is also a 2-byte instruction. Next is increment and decrement operations. Increment instruction represented opcode will be INR instruction. INR is represented for increment the register value, otherwise the memory value by 1. What is an operand for this instruction? Either it may be R represents any one of the 8-bit register, M represents any one of the any memory content value here. This is also a 1-byte instruction. Next one is INXM. INXOR, otherwise we can use INXM. So if we use an INXOR means the register content value will be incremented by 1. That will be represented as INX instruction. By using this instruction, the register pair value will be incremented by 1. Any kind of register pairs we can use, either the BC register pair or DE register pair, otherwise the HL register pair. Next one is the decrement instruction. This instruction is used to decrement the register, otherwise the memory, by value 1. That is the function of this DCR instruction. The content of register or memory location are decremented by 1. The result will be stored inside the same location area. If the operand is a memory location, its address is specified by the content of HL pair here. So this is also a 1-byte instruction. The next arithmetic instruction is DCX instruction. So DCX is always used to decrement the register pair value by 1. That is the function of this DCX instruction. The content of register pair are decremented by 1. The result is stored in the same location. That is the function of this arithmetic instruction here. So DCXH is a 1-byte instruction. Next is the logical instructions. So based upon the logical operations, if you want to perform in this 8085 microprocessor, then we prefer with this logical instructions only. So based upon these instructions, to perform logical operations on data, either it may be stored in the registers, otherwise the memory, otherwise it will be stored inside the flag status values. The various kinds of logical operations we can able to perform in this 8085 microprocessor. One is the AND OR logical operation, OR logical operation, XOR logical operation, then the rotate operation, the compare operation. Next one is the complement instructions are there. By using these operations, the various kinds of instructions are available here to perform these kind of operations. So any kind of 8-bit data, otherwise or any kind of register content value will be, we can do the basic logical operations here. Either we can do the AND operation, OR operation, otherwise the XOR operation. If you are doing these kind of operations, where the output values are stored, means it will be stored inside the accumulator only. So by using these instructions, easily we can able to compare the data for using the logical functions. Directly we can perform the AND logical function, OR logical function, otherwise the XOR logical function. What is the logical condition for these things? So based upon the logical condition only, the AND operation or otherwise the XOR logical operations will be taking place. The AND logical operation is, if any one of the input is 0, then the output value equal to 0. That is a logical condition for the AND gate operation. Next, OR operation means if any one of the input is true, then the output value is always true. That is a condition for the OR logical operation. Next is the XOR logical operation. So XOR logical operation means if both the inputs are same, then the output value equal to 0. If inputs are different, then the output value equal to 1. That is a logical condition for the XOR gate operation. By doing these kind of operations, where the output values are stored, means the output values are stored only inside the A register. Another name for the A register is accumulator. Next is the rotate instructions are there. So inside this logical instruction, there will be rotate instructions are there. By using the rotate instructions, we can able to shift the data either from the left hand side to right hand side, otherwise from right hand side to the left hand side. That is from least significant bit to most significant bit, otherwise from most significant bit position to the least significant bit position value. Easily we can able to transfer the data by using the instruction called rotate instructions. Next is the compare instruction. By using this compare instruction, we can able to compare the data. Either it may be the greater than value or lesser than or equal, we can able to compare here. The content will be stored inside either the register or otherwise the memory location. Easily we can able to compare the data here. So based upon the comparison of the accumulator content with any data or register, what will happen means the output value will be stored inside the flag status only. Any kind of compare instructions output value stored only in the flag status. Next one is the complement operation. By using this complement operations, what we can able to perform here means we can able to get the complement output values. What is complement? 0 value will be always replaced by 1 and 1 will be replaced by 0. That is said to be the complement operation. So each and every complement operations we can perform by using this complement instruction. Next is the logical instruction. In this logical instructions, the CMP instruction is that the CMP represents the compare. We are going to compare the two data. Either it may be the register with the accumulator, otherwise the memory with the accumulator. That is said to be a logical instructions. This compare the register or memory with the accumulator. And you see this instruction, what happens means the content of the operand or compared with the content of the accumulator. So based upon this comparison, both the contents are preserved here. The result of the comparison is shown by setting the flags of the program status word here. So based upon this, the logical conditions values will be there here. If the accumulator content is registered than the operand part, then the carry flag will become set conditions. So here the carry flag set condition means the carry flag value will be equal to 1. If it is reset means the carry flag value equal to 0. The next condition is if A is equal to register, otherwise any kind of memory content value in the operand means, then the 0 flag is a set condition. So automatically the 0 flag will become 1. If A is greater than either it may be the operand part means, then both the carry flag and the 0 flag are reset condition. That is the function of the logical instructions we are using. Example, CMPB. CMPB represents we are comparing the B register content with the A register, and the output value will be stored inside the, based upon this operation, the output value is stored inside the flag status. CPA. So initially we are comparing the data from the register, otherwise the memory location. Now we are going to compare directly the data with the accumulator content. The 8-bit data is compared with the content of accumulator here. The values being compared remain unchanged here. The result of the comparison is shown by setting the flags of the program status word here. What is the program status word here? Based upon the conditions, the flag status values will be changed here. If A is lesser than data, the carry flag will become set condition. If A equal to data means, then 0 flag will become set condition. If A is greater than the data means, then both the carry flag and 0 flag are at reset condition. So that is the output values will be changed, otherwise it will affect in the flag status. The next logical instruction is AND instruction. This logical AND register, otherwise it will be all memory with the accumulator. Yeah. Now we are going to do the AND logical operation. The AND logical operation can be done with the specified register. It will be specified in the operand part here. That is the accumulator content, otherwise the register content or memory content value will be compared here. The content of the accumulator are logically ANDed with the content of register or memory content. Where the results are stored, the result is placed inside the accumulator. If the operand part is a memory location, then its address is specified by the HL register pair here. So based upon these output values, the sign flag, 0 flag and then the parity flag are modified to reflect the result of the operation. Where the carry flag will become here, the carry flag is at reset condition and the auxiliary carry flag is at set condition. So based upon these conditions, the flag status values will be changed here. Example, for this logical instructions A and A, this opcode part and the operand part is B register or C or D register or E, any one of the register we can use. Otherwise directly we can use the memory M. So this is a 1 byte instruction. The next is AND immediate operation, directly we can able to do with the accumulator. Yeah, the instruction is A and I, operand part will be the 8-bit data. If we do this operation, what happens means the content of the accumulator are logically ANDed with the 8-bit data. The results are stored inside the accumulator. The sign flag, 0 flag, parity flag are modified to reflect the result here. At the same time, the carry flag is a reset condition and auxiliary carry flag is a set condition. Example for this logical instruction is ANI 86H. 86H is the hexadecimal value. This value will be compared with the A register content. The next logical instruction is XOR operator. The XOR operator opcode is XOR A. XOR A represents XOR operation. Where it will be do the operation here? In the operand part we have to represent. Either it may be the register, otherwise it may be the memory. If it is a register means we can use any kind of 8-bit registers. If it is a memory means any memory register will be used here. The content of the accumulator are XORed with the content of register of the memory. Either it may be the register we are going to compare with the accumulator, otherwise it will be compared with the memory content here. Where the result is stored here, the result is always placed inside the accumulator. At the same time, the carry flag and the auxiliary carry flag are at reset condition. If the operand part is memory location, its address is specified by the content of HL register pair. Simultaneously, the 0 flag, the sign flag and then the parity flag are modified to reflect the result of the particular operations. So this is also a 1 byte instruction. Example will be XOR A B or XOR A M. So first one B, XOR A B represents it is a operand part will be the register, XOR A M represents the operand part will be the memory content. Next is ORA. The ORA represents we are going to do the OR operation with the accumulator. So logical OR register, otherwise a logically OR memory with the accumulator content. So any one of the register content, otherwise the memory content will be OR operated with the A register. That is the function of this OR operation. The content of the accumulator or logically OR with the content of the register or memory here. The result is placed in the accumulator. If the operand is a memory location, then what will happen means the specified address value will be stored inside the HL register pair content. The sign flag, zero flag, parity flag are modified to reflect the result. Carry and auxiliary carry always at reset condition here. The next instruction is ORA instruction. ORA is the awkward part and the operand part is the 8-bit data. We are going to do the logical OR immediate with accumulator. The content of the accumulator are logically OR with the 8-bit data. The result is placed in the accumulator. The carry and auxiliary carry flag will become reset condition. The sign flag, zero flag, parity flag are modified to reflect the output value. The next is the XRA. The XRA instruction is always used to do the XOR operation with the A register here. That is, the XOR operation we are going to perform either it may be the register or memory with the accumulator. The output value is stored only inside the same accumulator only. Next, the rotate instructions we are using. The first one is the RLC instruction. The RLC is the awkward part and there is no operand part for this RLC instruction. What is the function of this instruction means? It must be used to rotate the accumulator left. That is the function of the RLC instruction. Each binary bit of the accumulator is rotated left by one position. Bit D7 is placed in the position of D0 as well as in the carry flag. That is the condition for this instruction. Carry flag is modified according to the bit D7 value. Here the sign flag, zero flag, parity flag, auxiliary carry flag are not affected. This is also a 1-byte instruction. The next logical instruction is RRC. RRC represents rotate accumulator right. Each binary bit of the accumulator is rotated by right by one position. So here what will happen means bit D0 is placed in the position of the bit D7 as well as in the stored inside the carry flag value. CY represents it is a carry flag. It will be modified according to the bit D0 value. So based upon that bit position D0 value, the carry flag values will be changed here. Here the sign flag, zero flag, parity flag and then the auxiliary carry flag cannot be changed. This is also a 1-byte instruction. The next logical instruction will be the RAL. RAL represents rotate accumulator left through carry value. So each and every time the binary bit position value of the accumulator is rotated left by one position through the carry flag value. So this bit D7 is placed in the carry flag and the carry flag is placed in the least significant bit position of D0 value. The carry is modified according to the bit D7 value. So the sign flag, zero flag, parity flag, auxiliary carry flag are not affected. So RAL is also a 1-byte instruction. Next is a RAR instruction. RAR represents rotate accumulator right through carry value. When you execute this instruction, what will happen means each and every time the binary bit of the accumulator is rotated right by one position through the carry value. Bit D0 is placed in the carry flag and the carry flag is placed in the most significant bit position of D7 value. Carry is modified according to bit D0. Both the sign flag, zero flag, parity flag, auxiliary carry flag are not affected here. This is also a 1-byte instruction. The next logical instruction is a complement instruction. This instruction is used to get the complement values. So it can able to get the accumulator complement values. So CMA represents complement the accumulator. Here the flag status values cannot be affected here. Next logical instruction is CMC. CMC represents complement the carry. Here we are going to get the complement value. The carry flag is complemented, no other flags are affected. Example will be the CMC instruction. It is used to get the complementary value of the carry flag. The next logical instruction is STC. The STC represents set carry value. If the carry flag is a reset condition, if we want to change it to the set condition, then we have to do the STC instruction. When you execute this instruction, what will happen means the carry flag will goes to the set condition. Other flags cannot be affected when you are executing this STC instruction. This is also a 1-byte instruction. Next is the branching instruction. So branching instruction always used to alter the normal sequence or flow here. If any sequential flow will be taking place normally, then if you want to distract that, then always we prefer the branching instructions. These instructions alter either conditionally or unconditionally. That is the function of the branching instructions we are using. The example will be the JMP instruction. JMP represents jump instruction. It is an unconditional jump instruction. The JMP is the opcode part and operand part will be the 16-bit address. When I execute this instruction, what will happen means the program control without checking any conditions directly goes to the specified operand part. That is the function of this JMP instruction. So this JMP instruction having a 3-byte instruction. Example is JMP 2034H. It represents, this instruction will have a unconditional jump having. Next is the JX. JX represents, it is said to be a jump conditionally. The opcode is J and then the operand part is 16-bit address. Here the program sequence is transferred to the memory location, the specified by the 16-bit address given in the operand based on the specified flag or the PSW register. So any kind of flag status we can use here, either it may be the 0 flag or sign flag or carry flag or parity flag we can use here. Here we cannot be able to use with the auxiliary carry flag. Example, in the X place we can be able to put the Z. Z represents it is a 0 flag. So if you want to check the condition of the 0 flag, then we have to put JZ, jump on 0. Where it goes, if condition is true, it goes to the specified 16-bit memory address, it will be exist in the operand part. So that is the function of this JZ instruction. That is said to be a conditional jump instruction. So these are the few examples for the jump conditional here. That is the conditional jump instructions. The outputs are JC. JC represents jump if carry. Whenever the carry flag is at set condition, then only the program control transfer to the specified memory location. That is the function of the jump carry instruction. Next one is JNC. JNC represents jump if no carry. Whenever the carry flag equal to 0, then the condition is true, otherwise the condition is false here. Next instruction is JNC. JNC represents jump if no carry. Whenever the carry flag is at reset conditions, then the condition is true, otherwise the condition is false. Next is JP. JP represents jump if positive. When the result will be positive here, whenever the sign flag equal to 0 means, then only the result is positive, otherwise the result will be negative. Next is JM. JM represents jump if minus. Whenever the sign flag equal to 1, then automatically it will be represented as a negative number. At that time only the condition is true, otherwise the condition is false here. Next is JZ. JZ represents jump if 0. Whenever the 0 flag is at set condition, then the condition is true, otherwise the condition is false here. Next is JZ. JZ represents jump if 0. Whenever the 0 flag is at set condition, then only the condition is true, otherwise the condition is false here. It will execute the next instruction. Next is JNZ. JNZ represents jump on no 0. Whenever the 0 flag is at reset condition, then the condition is true. Next is JP. JP represents jump if parity bit is even. If the number of ones in the accumulator content is even means, then the condition is true, otherwise the condition is false. That is a logical condition for this JP instruction. Next one is the JPO instruction. JPO represents jump if parity odd. Whenever the odd parity bit, when the odd parity bits exist, if the accumulator content number of ones is odd number of ones, then automatically we can say it is said to be a parity bit, odd parity bit. Then only the condition is true, otherwise the condition is false here. The next branching instruction is the call instruction. So unconditionally, if you want to call the subroutine means, then we have to use the call instruction. Call is the opcode part and the operand part is 16-bit address. When I execute this instruction, the program sequence is transferred to the memory location specified by the 16-bit address. It will be stored inside the operand part. Before the transfer, the address of the next instruction after the call is pushed onto the stack pointer. So that is the function of the call instruction. This is a 3-byte instruction. It takes more time for execution when compared to the 1-byte or 2-byte instruction. Next branching instruction is CX. The program sequence is transferred to the memory location specified by the 16-bit address given in the operand based on the specific flag of the program status word. Before the transfer, the address of the next instruction after the call is pushed onto the stack. That is the function of the So instructions we are using. Next one is call conditionally. How can we call conditionally? By using the instruction called CC. CC is always used to call unconditionally here. So CC means if carry. Whenever the carries exist, then only the condition is true, otherwise the condition is false for this instruction. Next is CNC. CNC represents call if no carry. Whenever the carry does not exist here, then only the condition is true, otherwise the condition is false. Next one is CP. CP represents call if positive. Whenever the sign flag equal to 0, then only the condition is true, otherwise the condition is false. Next one is CM. CM represents call if minus. Whenever the sign flag equal to 1, then the condition is true, otherwise the condition is false. Next one is CZ. CZ represents call if 0. If 0 flag equal to 1, then the condition is true, the condition is false here. Next one is CNZ. CNZ represents call if no 0. So call if no 0 means the 0 flag is a reset condition. Then only we can say it is a way call if no 0 value. Next is CPE. CP represents call if parity even. Call if parity bit will become even. When the parity bit will become even? So by using the accumulator content, otherwise by checking the accumulator content, if the number of ones is even, then the condition is true, otherwise the condition is false. Next is CPU. CPU represents call if parity is odd. When the accumulator content number of ones or odd parity bit, then only the condition is true, otherwise the condition is false here. Next one is the return instruction. So the return instruction is always used at the end of the subroutine. It will be used for the unconditional return instruction. The program sequence is transferred from the subroutine to the calling program. The 2 bytes from the top of the stack are copied into the program counter and the program execution begins at the new address. Example for this instruction is RET. Next is the RX instruction. The program sequence is transferred from the subroutine to the calling program based on the specific flag of the program status word here. This is an example for the unconditional. Otherwise, you can say it is said to be it will be used for the call conditionally here. Based upon the condition only, we can able to transfer the data. Otherwise, you can able to move the memory content location from one location to another location. The 2 bytes from the top of the stack are copied into the program counter and program execution begins at the new address. Next one is the conditional return instruction. RC represents return if carry. Whenever the carry flag equal to 1, then the condition is true. Otherwise, the condition is false here. Next is RNC. RNC represents return if no carry. Whenever the carry flag also equal to 0, then the condition is true. Otherwise, the condition is false here. Next is return if positive. Whenever the sign flag equal to 0, the condition is false. Otherwise, the condition is RP represents return if positive. Whenever the sign flag equal to 0, the condition is for true. Then the program will transfer to the specified memory location. Otherwise, the program will execute the next instruction. Next is RM instruction. RM represents return if minus. Whenever the sign flag equal to 1, then it will be considered as a negative number. At that time only the condition is true. Otherwise, the condition is false. Next is RZ. RZ represents return if 0. Whenever the 0 flag is at set condition, the condition is true. Otherwise, the condition is false. Next is RNZ. RNZ represents return if non-zero. Whenever the 0 flag is at reset condition, then the condition is true. Otherwise, the condition is false. Next is RPE. RPE represents return if parity bit is even. When the parity bit is even, if the accumulator content number of ones is even, then only the parity bit will become even. Otherwise, the condition is false here. Next one is RPO. RPO represents return if parity bit is odd. That is, the P equal to 0 means then only the condition is true, otherwise the condition is false here. P represents the parity flag, Z represents the 0 flag, and S represents the sign flag, and CY represents the carry flag. AC represents the auxiliary carry flag. For any kind of conditional operations, here we cannot use the auxiliary carry flag. Other flags will be used for checking the conditions in this 8085 microprocessor. The next branching instruction will be RST instruction. The RST represents it is a restart instruction. There are 8 restart instructions are available here. It will be another name for these instructions are software interrupts. The interrupt will be given to the microprocessor by using this RST instruction. It starts with from RST0 to RST7. So totally 8 instructions are available for the restart operations here. The RST instruction jumps the control out to one of 8 memory locations depending upon the predefined numbers are there. These are used as a software instructions in a program to transfer program execution to any one of the 8 locations. That is the function of these instructions we are using. Example for this instruction is opcode is RST and operand part is the numbers from 0 to 7. Any one of the value we can able to put here. Next is the restart address tables are there. So each and every RST instructions will have a different memory location. So each and every instructions having the 8-bit memory locations are available here. For RST0, that is restart 0 instructions will have a address from 00002 to 0007. That is the instruction address for the RST0. The next 8 values will be used for the RST1 from 008 to 009. And then from RST2 will be 0010. It starts with 10 hexadecimal value. Then RST3 will have the 0018 hexadecimal value. Then RST4 0020 hexadecimal value. Then RST5 is 0028 hexadecimal value. Then RST6 is 0030 hexadecimal value. Then RST7 will have a memory address value will be 0038. While executing these kind of restart instructions, what will happen means the program control directly goes to the predefined memory address location. For example, if you are executing the RST4 instruction, what will happen means the program control goes to the memory location called 0020 memory location. That is the function of this software instructions here. The next control instructions, that is the machine control instruction. The machine control instructions always used to control the operation of this 8085 microprocessor. If you want to control this processor, then we have to use this machine control instructions only. Then only we can able to do the controlling of this 8085 microprocessor. The first instruction here is NOP instruction. NOP represents no operation. It consists only the opcode part, there is no operand part. So it is said to be a 1-byte instruction. So in executing this instruction, what will happen is the no operation will be performed here. The instruction will be fetched and then it will be decoded, but no operation will be executed here. That is the function of this NOP instruction. It will be used inside the programs. Next is the halt instruction. The opcode is HLT. So this is also having only an opcode part. There is no operand part here. This is also a 1-byte instruction. When I execute this instruction, the CPU finishes executing the current instruction and halts any further execution. That is, the program execution will be stopped whenever it reaches the instruction called HLT instruction in the 8085 microprocessor. During that time, what happens means an interrupt, otherwise a reset is necessary to exit from the halt state. That is the function of this halt instructions we are using. The next is the DA instruction. So this is also a machine control instruction. DA represents disable interrupt. So this is also a 1-byte instruction. The interrupt enable flip-flop is reset and all the interrupts except the trap are disabled. That is the function of this control DA instruction. Next is the EA instruction. EA represents enable interrupt. The interrupt enable flip-flop will become set condition and all interrupts are enabled here. That is the function of the interrupt enable. The no flags cannot be affected here. The instruction is necessary to re-enable the interrupts except the trap interrupt signal. Next is the RIM. RIM represents read interrupt mask. So this is also a machine control instruction. This is also a 1-byte instruction. This is a multi-purpose instruction used to read the status of interrupts, either it may be 7.5, 6.5, 5.5 and read serial data input bit values. The instruction loads 8 bits in the accumulator with the following interpretations. Example for this instruction will be only the opcode we have tried it is RIM. It is used to read the interrupt mask. So each and every interrupt instruction will have 8-bit positions are available from D0 to D7. The D7 represents it is a serial input data bit we have to give here. That is represented SID. SID represents the serial input data. Bit D6 and then D5, D4 will be used for the interrupt signals I7, I6 and then I5. Next, bit D3 will be used for the interrupt enable flip-flop is set condition. That is if bit equal to 1. If bit equal to 0 means it will become reset condition. Next, D2, D1 and D0. These three are used for the RST 7.5, RST 6.5 and then the RST 5.5 instructions. These interrupt mask if bit equal to 1. So that is the function of this read interrupt mask instruction. Next one is the SIM. SIM represents here a set interrupt mask. This is also a multi-purpose instruction and used to implement the 8085 interrupts, the 7.5, 6.5, 5.5 and serial data output. The instruction interrupts the accumulator content as follows here. Thank you.